No.
So I think we can start. So good morning, everyone. Today, we have the pleasure to have here with us Mahilou Gendron-Marsolais. So Mahilou, she's an expert on radio observations on galaxy clusters, and she has been actively engaged in the Spanish participation on the Square Kilometer Array Observatory, where she acts as SKA Science Community Manager here in Spain. Mahilou obtained her PhD in astronomy in 2019 in the Université de Montréal in Canada. And after her PhD, she was awarded the ESO fellowship. She chose to go to Santiago in Chile, where she was also sharing her time between her work on galaxy clusters and at the duty times in the AUMA Observatory. So as an ESO fellow, she served as an astronomer on duty at the AUMA Operation Support Facility. She performed data quality and calibration assessment, as well as software testing, and she's also part of the VLBI AUMA team, preparing and delivering these special observations. She's now currently a postdoc researcher at the Instituto de Astrofísica de Andalucía in Granada since December 2021, and she's working with Lourdes Verdes Montenegro as part of her team coordinating the Spanish participation as KO. Unfortunately, we will meet Mahilou in Spain because in May she's moving back to Canada because she recently got an assistant professor position at the Université Laval in Quebec City. And Mahilou's research focuses on the complex relation between supermassive black holes located at the center of galaxies and their environment using multi-wavelength observations. She's also passionate about science outreach and solving the issues of diversity in science. So Mahilou, the floor is yours.
The microphone works well. I think so. Okay. Thank you so much for this beautiful introduction. I'm very happy to be here. It's been a long time that I want to come to the IAC to meet you guys to talk about my research. So it's finally happening. I'm gonna leave Spain soon, but if I still want to maintain collaboration, of course. My title is a radio eye on galaxy clusters, and what I want to do with you today is kind of to share what a radio telescope can see when they look at galaxy clusters, because we have made a lot of progress in this field recently. And well, it's very specific, and I don't think most of the people actually know what we have discovered in this very interesting environment. And so I want to give you like an update on that. So it's going to be very general, and I hope that everyone can follow the talk, basically. So let's see here. Yes. So this is the outline of my talk. I'm going to start, actually, most of my talk is going to be like an introduction on galaxy clusters. I have added some special slides because I am here. Last week I was observing at the GTC, so I kind of want to give you some special slides, special results on that. And then I'm going to talk a little bit more about what I mean by recent advances on radio observation. What are the new open questions that we have? And then during all my talk, I'm really going to focus on one galaxy cluster, my favorite one, which is the Perseus cluster. And I think during the talk, you will understand why it is such an amazing cluster to study. And then finally, I'm going to open a little bit on what is the future of these studies. I want to start with this beautiful image. Do you guys know which telescope took this image? Do you recognize it? Yes, Euclid, exactly. So it was one of the first, the 5 first images that were released with Euclid. And I was really surprised when I saw that one of the 5 is not only a galaxy cluster, but it is my galaxy cluster, the Perseus cluster. Oh my God, what an honor, right? So I'm gonna use this image in the background of my slide to explain to you a little bit what are galaxy clusters. So they are made, of course, of thousands of galaxies, very massive. They extend on megaparsec scales. And we usually identify in the center what we call a BCG, a brightest cluster galaxy. In this case, it is, in the case of Perseus, it is this galaxy here, NGC 1275. In terms of mass distribution, of course, the main component of the mass is the dark matter component, and then the galaxy, but then there is this other component that we don't perhaps talk a lot about, and it's what we call the intracluster medium, or the ICM. And this is an actual image taken with Chandra of the Perseus cluster. So I've overlaid it on top of the Euclid image. These are 400 hours of exposure with Chandra, right? It's the X-ray brightest cluster in the sky. So it's very well studied with Chandra. And you see a lot of structure inside those, inside this intracluster medium. The intracluster medium is a hot diffuse plasma that will fill cluster centers. They are very bright at X-ray wavelength. And so when you look at them with the X-ray telescope, you will see them as a diffuse sources in the sky, like Perseus, for example. And actually, they are so X-ray bright that all of this gas should be cooling down onto the brightest cluster galaxy very rapidly. But this is not what we observe. There is something that keep this gas hot, and we call this the AGN feedback process, right? Which kind of inject, so the central galaxy here inject somehow energy into this intracluster medium and keep it as it is. How does it work exactly? AGN feedback, it is quite complex, so I'm gonna tell you a little bit more about that. But basically, you know, all of these galaxies inside have a supermassive black hole. Of course, a subset of those supermassive black hole are active, so they are accreting matter. And in some cases, they produce these jets of relativistic electrons that are inside magnetic fields. And these two things, magnetic fields and relativistic electrons, will produce synchrotron emission. And in those cases, in the cases of those systems, given the strength of the magnetic field and the energy of those particles, this synchrotron emission will be visible at around 1 gigahertz, so radio emission. So during my whole talk, I'm going to be talking about radio emission. What I mean by that is this particular synchrotron emission. Okay. The spectrum of this emission is, of course, the combination of the spectrum of the emission of each of those individual electrons put together. And if you have a power law distribution in energy of those electrons, you will get a power law spectrum of the synchrotron emission. And this slope here, which we call the spectral index, alpha here, is very useful for us to study the population of electron. So for example, if you are looking directly at the AGN here, you have very energetic electrons, right? They are emitting up to higher frequency, and then you will have a flatter spectrum. If you look further from the jets, you will have electrons that are more tired, let's say. They have emitted more energy, and so the spectrum here will get steeper. So this spectral index that you may have heard of is really important for us to study, for example, to estimate the age of the population of electron that we are studying. Okay, so what do those jets look like? You have seen those images, I am sure, before. These are a spectacular example of radio jets that you find in the center of galaxy clusters. These are the ones inside Perseus. They are a little bit less impressive, I guess. These are the two radial lobes here, but they are quite extended, right? And so they will encounter this component that I was telling you about, this intracluster medium that I'm showing here in blue. These are all Chandra observation, I think. And so you can really see how those radio jets push away the cluster gas. And this is all the mechanical AGN feedback process. And it's quite remarkable, right? Because you have a supermassive black hole hidden inside the central galaxy of a cluster, and it's somehow ruling the entire dynamic of a galaxy cluster. Okay, now I'm gonna tell you a little bit about some optical stuff, because I think I consider myself as a radio astronomer, but sometimes I do optical things. And yeah, so this is what I was doing last week here, because I really got interested into the brightest cluster galaxies, because in optical, they are really interesting. These brightest cluster galaxies lies in those special environment, right? They are a little bit special. They are the most massive galaxies. And in many cases, they show these extended optical emission line filaments. These are some information about those. They can be very extended, very thin. They're quite luminous. We can also observe them in molecular gas in soft X-ray emission. So they are multi-phase filaments. And we find them in almost all of the most relaxed, what we call cool core clusters. These are other examples in other galaxy clusters. So how do they form? Why are they there? They are likely a key step in this whole AGN feedback process. There are many models that try to explain their formation. I would say that the main one is that we think that these filaments are formed from the condensation of the intracluster medium. They condensate into these filaments and then they feed the supermassive black hole, which emit those radio jets. So it's kind of closing this whole AGN feedback loop. This is currently, I would say, the main idea to explain those filaments. But they are definitely linked to the intracluster medium, right? Because they are always at the center of these galaxy, of these clusters, I mean. And so it would be very useful to study the dynamics of those filaments. And so to do that, we need optical IFU observation. The thing is that the one in Perseus, since it's so nearby, it's actually 4 arc-minute in the sky. And so until a few years ago, there was never any complete velocity maps of those filaments. And so I started to work on those with an instrument called CITEL, which is an optical imaging Fourier transform spectrometer at CFHT. And it has a field of view of 11 by 11 arc-minutes, right? And so what I'm going to show you is a video going through the cube, because this is what's cool when you have a cube, is to make those videos, right? And you will see the main emission line from this nebula. So you will see first the N2 lines, 1 second, right here, and then H alpha, N2. There's a foreground galaxy that is falling inside the cluster. There's a bit more redshifted. And then finally, at the end of this filter, you have the 2 S2 lines. So with these data, we were able to make the first complete velocity map of these filaments. We even have more higher spectral resolution observation now, other filters, so we keep working on that. But one thing also that my collaborators start to do is start to analyze those velocity maps. This is the velocity map of the filaments that we obtained. In the background, in gray, you see the Chandra observation with the cavities and everything. And so they start to study the velocity structure function of these filaments. So these plots are made out of you basically take the separation of pixel pairs in the velocity map and you compute the average absolute value of their velocity difference. This is what you see on this axis, and you have those curves. And depending on the amplitude, the different features that you can see, you can kind of analyze what kind of motion or what are the scales that are driving the motions of these filaments. And we have done that for Perseus. My collaborator have done that on many other clusters now based on Muse observation, for example. And in all of those cases, it suggests, these BSF suggest that the supermassive black hole is actually responsible mainly for driving these kind of motion. So that's nice, but there was one cluster, very famous, the Virgo cluster, which only had partial velocity map. Again, it's a very nearby cluster like Perseus, and it's so big that this is the Muse field of view. You have the velocity map here, but all of these other filaments are out. We don't have any velocity information. Yes, you may not recognize, but this is M87, right? You have the jet that is here. This is continuum subtracted, but you have all these beautiful filaments in M87. And so I wanted to know more about these filaments in two places in particular. Here you have the only molecular detection in those filaments. And here you have those filaments that are completely detached. And they are located in a second outburst of the Central Aegean. So it's a quite interesting place to study the dynamics. If it's different from there, we don't know. And so I was allocated Megara time on GTC. This is the field of view of Megara. And so that's why I am here, and I was observing those cubes last week. And so I wanted to present you some very preliminary results where you can see the same lines as I was showing you in the other in Perseus. And so very preliminary result. This is going to be the project of my master's student. She's going to start in May working on that, but we are very excited about those observations. Okay, so back on the main program. This was the optical side of the talk, I guess. So I've talked a lot about these BCGs, the radio jet, the AGN feedback, these filaments, all of these things. But there's actually other radio galaxies inside the Perseus cluster. There's at least, for example, these three ones here. So these are galaxies with radio jets. What do they look like? They look like this. This is I kind of want to present you this in a historical way. So I'm going to go through the history of the Perseus cluster in radio wavelength. And so this is the central galaxy. The little radio lobes are here. This is a very bright source, actually. And then there is these two other radio galaxies that are part of the Perseus cluster, 1265 and IC310. And you can see that they have like these head-tail morphologies, right? Very strange. And in this paper, which dates back to like more than 50 years ago. Okay, so I'm not the only one that have been studying Perseus. It's been a very long time that we've been studying these galaxies. But in this paper, they suggest that maybe there's some sort of wind coming from that galaxy, and it kind of impacts those galaxies, and it creates those shapes. That was like the first hypothesis that he had. But then later, they had more observation of the Perseus cluster, and they found, they found this other radio galaxy, much smaller, CR15. But as you can see, it is pointing, it's not radial at all, right? It's pointing in another complete, other different direction. So it completely rules out the first hypothesis to explain those. And so this suggests in this paper a new explanation, and this is exactly what is in the paper. This suggests that these are radio galaxies in their own right, okay? And that the direction and form of the radio tail also suggest a motion of a radio galaxy resisted through a gaseous medium. So they are going through something. What is this gaseous medium? Well, it's the intracluster medium, right? This purple thing that I was showing you earlier. And it's quite remarkable because in those same years, they were starting for the first time to observe galaxy clusters with X-ray telescope, the first X-ray telescopes. And they were finding the intracluster medium because they were detecting it for the first time in Perseus, Coma, Virgo cluster, the nearby galaxy cluster. And then, radio observation of other radio galaxies with all twisted, different morphologies. So what's happening with these bent jet radio galaxies? Well, we think that they are just normal radio galaxies with two jets, but they are going through the intracluster medium, or the intracluster medium is moving, and then it's basically bending the jets backward, as you can see in this simulation. And the higher the relative velocity between the galaxy and the intracluster medium, the higher the ram pressure, the more bent the jets are going to be. This is the idea that we have. And based on that, of course, the way we classify them is based on the degree of bending of those jets. So we go from wide angle tail to narrow angle tail to head tail radio galaxies. So you may have seen these kind of names in the literature. So let's try for fun to classify the prototype of this band jet radio galaxy, which is NGC 1265, which is located in the Perseus cluster. Well, based on those observations, I would say that it's a narrow angle tail, right? More or less. But imagine that you had only very high resolution observation of that are not very deep. You would miss completely the rest of the tail, and then it looked like a wide angle tail, no? And if you had only very low resolution observation of this source, like we had back in the days, well, it looked more like a head tail. So it's a bit problematic, right? This classification. It doesn't take account also projection effect. It depends highly on the type of observation that you have. So these sources, sometimes their name will change as we get better observation. The trajectory of the jets are assumed to be orthogonal to the motion, right? But it's not always the case, as you can see, for example, in those simulations. So of course, this is the best we can do, right, with this classification, but it's a bit misleading sometimes. And it's even more complicated because if you really look at galaxy cluster with a radio telescope, this is actually what you will see. You will see not only radio galaxies, but you will see diffuse radio structures that are, hundreds of kiloparsec up to 1 megaparsec. This is Perseus. This is a merging cluster where you can see giant radio halo or relics. This is how we call these, like things that we found at the outskirts of cluster. This is 1 megaparsec. Okay, so these are 1 megaparsec scale diffuse radio structure, and we find this in many, many, many galaxy clusters now. And it's a bit problematic, no? So where this emission come from? Because all of this, as I said, is synchrotron emission. So you need magnetic fields. That's okay, probably magnetic fields are everywhere in galaxy cluster, but you need relativistic electrons. And as those electrons are traveling through the cluster from the AGN to the outskirts, like I said, they lose energy. And so we should not be able to see a synchrotron emission, let's say here, so far from where they were accelerated. So somehow there is some energy, that reaccelerates, some sort of energy that reaccelerate these particles, so we can see those very large features. Okay? So there is no AGN there. There's just this radio emission. The answer, what is that source of energy? It's probably due to the intracluster medium, because the intracluster medium is not quiet, right? Galaxy clusters are internally perturbed by this old AGN feedback. They are interacting with galaxies that are infalling or galaxy groups, things like that. So this intracluster medium is not smooth at all. It is full of structure. So I'm going to show you a simulation here of what we could see of a galaxy cluster in X-ray. A galaxy cluster with an AGN outburst, let's say, and that is at the same time interacting with a group that is falling inside the cluster. And you will see that it creates all sorts of feature. And on this side, you will follow the electrons released by the central AGN. And so you can see that there's like these spiraling structures that appears in the ICM, the intracluster medium. And also you can see that these electrons are completely spread around the entire cluster. And now we think that these ICM motions are enough to reaccelerate these particles so that we see them again on very large scales, potentially doing these kind of relics, for example, or these halo emission. So this is a very recent idea that we have of galaxy clusters. Okay, so overall, synchrotron emission in galaxy cluster is not only found in the central galaxy. There is other radio galaxy that can be very interesting. And also there is these diffuse radio sources that we try to explain, right? We want to understand. As I mentioned, we have made a lot of progress recently in radio observation of galaxy cluster, and this is due to several factors. First of all, we have many more radio facilities that are sensitive at very low frequencies, okay? So, and this is important because if you remember the spectrum, these sources are brighter at low radio frequencies. So now that we can observe below 1 gigahertz, 100 megahertz, these kind of frequencies, we are starting to see all of these tired electrons, right? We are starting to capture them. The bandwidth of the receiver on these telescopes also is increased, so we are more sensitive. The imaging algorithms that we have are much better, and so we are starting to see many things. I'm going to show you a couple of examples of things that we see in galaxy clusters. You may have seen these images in different press releases. These are the two most famous relics, the sausage relic and the toothbrush relic, right? Very nice names. It makes sense, I guess. This is a famous cluster as well. There is this halo emission full of filaments. This is a head-tail radio galaxy that is very long. This is like 500 kiloparsec. So it's stay collimated, very thin collimated on all of that distance, and we don't know why. Another head-tail, very long head-tail radio galaxy. Another one here that is full of different structures. This is a galaxy group. You may think that galaxy group are like more quiet or whatever, but no, they're crazy as well. In pink, you can see the radio emission, probably from different outbursts of this central region, but it kind of do this like square filaments structures. This is another Abel cluster, radio phoenix, which are like patches of radio emission very far from agents, probably again reaccelerated by ICM motions. So weird stuff, right? Very weird stuff. So how do we put all of this together? This is like the main question. First of all, how do we classify these sources? They are so different. Their morphology are very different, and it's quite challenging. What are their origin, of course? How do we put together cluster properties and radio properties? What is the distribution and strength of the magnetic fields across galaxy clusters? I'm not going to answer those questions. I'm sorry, of course. But these are new questions that we have after, based on these observations. Okay, let's focus now on one cluster, Perseus, of course. As I said, it's the X-ray brightest cluster in the sky. It's very near, only 70 megaparsec away. It has those beautiful cavity systems. It is the host of several benjet radio galaxies. So obviously, it's a very interesting laboratory. And now, what I've been working on since many years, actually, I started at the very beginning of my PhD, is to work on VLA observation of this object. And with the time, we have gathered up to from very low frequency, 230 megahertz, up to 8 gigahertz observation of this galaxy cluster. This is very much a work in progress. Still, I'm not gonna show you these observation yet. Mainly, I'm gonna focus on these ones. It's very long to make those images. It's very complicated. Because the center of the Perseus cluster is extremely bright. It's 3C84. Maybe some of you may know this source because it's an actual calibrator that people can use in radio observation. And it's nice, but for me, it's a nightmare, right? Because I want to see the very faint emission that is next to this extremely bright source. And so you need to reach very high dynamic range, and any mistake in calibration, any RFI in the observation gets amplified, and it's quite challenging, to be honest. So eventually, I will have all of these observations done. But so far, we have already discovered many, many things. So these are the three of the maps that we have made of the Perseus cluster. Basically, in a little bit more detail, at the center here, you have the famous 3C84, very bright AGN. You have the little radio jets here. You have this mini halo emission at the center of the Perseus cluster. And you have these four, there is more, but there's these four main, I would say, benjet radio galaxies, so other radio galaxies inside that cluster. So what I'm going to do now is I'm going to go through, present you like the results that we have obtained with those VLA observation. one by one. So the main, let's say, results, okay? The first result that we published was about this mini halo emission. So halo, as I said, are found in many galaxy cluster in the center. In relaxed Kukulkan cluster like Perseus, we call them, they are smaller, so we call them mini halo. We know many of them. Perseus is like the closest one. But in general, they all look like a blob of radio emission in the center of the cluster. But in this case, since it is so nearby, probably, we can detect many substructure inside that mini halo. And this has not been seen, as far as I know, it has not been seen in other mini halo, or not at this level. So this is the first result that we published with those. We had new observation of NGC 1265. This is a very famous, like a prototype of these bandjet radio galaxies. You can see a lot of filaments that we resolve into this tail. And interestingly, when you look at lower resolution, where you pick up more like the diffuse faint emission from this galaxy, you can see the whole like extension of the tail. And this is like bending on almost like a full circle. And we see filaments as well along this extension of the tail. We don't know, to be honest, how this galaxy can have this shape, right? You cannot really explain that based only on the orbit of the galaxy throughout the cluster. There must be some, I don't know, intracluster medium motion there that is creating this thing. It has been suggested that perhaps it went through a shock or something like that. Unfortunately, it's quite far from the cluster center, so there's not a lot of intracluster medium gas, so it's quite faint, the X-ray emission, so we cannot really see what's happening there. Another curious case and quite surprising case in the Perseus cluster is IC310. So at the beginning, it was not my favorite, I must say, galaxy. It was just this head-tail sources. It was known 50 years ago, right? And that's it. But then, interestingly, when we look at our VLA observation, and especially at higher frequency, which we have higher resolution, we started to see this like gap here. And so it looks like it is actually a bandjet radio galaxy. And when you look at it with sufficiently high resolution, you can actually resolve two jets in that part here, right? Because it's a bit more faint, so it's a bit harder. It was a bit harder to resolve before, but with the VLA we see this, and that's great. I mean, it's there's some studies of other head tail like this, and usually when you look at it with a high resolution observation, you're kind of able to resolve these two jets. I say usually because in the case of this head tail here, we don't. This is just a one-sided jet, so it's very mysterious, this object. And as I was going through the literature, looking at this galaxy, because I thought, this is great, we see two jets in that galaxy, it's a bent jet radio galaxy, there's nothing more to say. And then I found out that there's this whole community of people that are studying IC310 because it's a blazar. It emits gamma rays. It is detected at quite high energy, actually. And so for these people, there was one jet, right, in the before. And so for these people, it's just like an engine and a jet pointing towards us. And that's why we see this blazar emission. It's a blaze, right? But now we see two jets. So two jets on the same side, not one jet pointing towards us. So how do we put this together? We thought about a possible interpretation for this. I made like a little drawing here. But basically, I mean, these jets are really, really close to each other. They are so close that it's like very high, unlikely that they are so bent, right? This would mean an extreme bending even inside the galaxy. And so probably that what we are seeing is projected. That probably IC310 looks more like a normal narrow angle tail radio galaxy, but we are seeing it this way. So instead of being like this, we are seeing it like this on the side, right? And so the jets appear closer to each other, but they are not in reality. And this way also we would see as well directly through towards the central massive black hole where the gamma rays are coming from. So this is a possibility that we have thinking about. But it's the only blazar bandjet radio galaxy that we know of. I don't know if there is other. It's quite difficult to find them because, well, gamma rays are difficult to detect in general. But so let's see what we find more with this galaxy. And then the last galaxy that I want to talk about is NGC 1272. It is this galaxy here at the very limit of this halo emission. You have the central galaxy here. This is kind of the neighbor big elliptical galaxy. And it has been known for a while as well as a wide-angle tail radio galaxy. So you can see here the jets of that galaxy. It looks like a little boomerang shape. Okay, so it's like slightly bent. And that's about it. This is the emission from the mini halo that is starting here, right? It's kind of very close to the mini halo, so it was like a bit interesting, I guess. But this is all what we could see at 350 megahertz with the VLA. This is the highest, this is in the A arrays, the highest resolution that we could get. And so we looked at L-band observation, so 1.5 gigahertz, slightly higher frequency, slightly higher resolution. And this is what we resolved. And none of us were expecting that, really. So what you see here is actually this thing here, okay? So the bent jets here, but this thing seems to be connected to this whole part here. So there's like this winding channel of emission, this eddy-like structure, and these lobes. So all of this is located in the square. So all of this purple thing, well, pink thing here is actually not the mini halo. It's the tail of that radio galaxy. Okay? Somehow in front of the bent jet. Okay? Very strange structure. But this is interesting because we found this in Perseus, but then there's more and more cases where we see, like, for example, this one is a radio galaxy. We don't resolve it, it's like a head tail, but you know, it's very nearby this halo. In this case, you have an AGN very close to a relic. So it looks like these radio galaxies that are not the central one, okay, that they are farther distributed in the galaxy cluster. It looks like they are actually contributing to these diffuse radio emissions. So the electrons that they accelerate, they also diffuse inside the intracluster medium. And they also probably are related to these large sources that we are observing. So these are bench-jet radio galaxy play an important role, probably. We tried to understand what we were seeing, right, in that very weird tail. So I made this composite image where I kept only in red the radio observation from this galaxy. And in the background, this is the central galaxy, this is the host galaxy of this tail. And you know, the weird thing is, how can we have like these bent jets in front of the tail? It's a bit strange, right? Perhaps it's a projection effect, we don't know exactly. Perhaps we are capturing this galaxy as it is moving, like turning around in the cluster. So we're looking this way, and so the jets are projected in front of the rest of the tail. So this is like closer to us than this, for example. We don't know. It's a possibility. Another interesting point to note is when we overlay on top of this, the Chandra, the very deep, beautiful Chandra observation of Perseus. You have the cavity system here, and then you have this spiral structure that we call cold front that you could see in the simulation at the beginning. As I was saying, there's lots of interaction in the intracluster medium. It's very moving and everything. And so probably that in Perseus, there is like a group or a couple of massive galaxies that are falling inside that we see actually in the Euclid image. And this is disturbing the intracluster medium and creating this sloshing, we call it sloshing motion. And so we have these cold front discontinuity inside the intracluster medium. And so these are kiloparsec wide surface with strong velocity shear, right? Of course, everything is projected, but it really cut this tail in two parts, right? There's this more collimated part and there's this more diffuse part. So ideally we would like to have like simulation of what happened when a radio galaxy go through this kind of discontinuity. But this, I mean, this kind of correspondence between both structures is quite interesting. And we also we also noted similarities between, especially this part of the tail and a Kármán vortex street. Kármán vortex street are these swirling vortices that we see in nature on different scales. Actually, the Canary Islands are making this quite, if you Google it, you will find this very easily. And so so it happens in the clouds, and so why not in galaxies, I guess. But if you can imagine that this galaxy is going through the cluster and it's creating a wake inside the intracluster medium, and the synchrotron emission that you see is tracing the wake that is inside the intracluster medium. And so it's definitely not laminar. We don't know if it's a Kármán vortex street, if it's a turbulent flow, but that gives us important insights into the viscosity of the intracluster medium, which currently we cannot really constrain based on the Chandra or X-ray observation of this gas. So that was a cool result. And as well, we are finding more of these oscillating radio galaxies in many galaxy clusters. So overall, I think we can all agree that FIRST is an amazing laboratory, right? We have found many things, many new things, even though we have been studying this cluster for 50 years. And probably we're going to even find more things with these higher frequency observation. Now, if we look in the future, it's going to be even more crazy, I guess, because we're going to have, for example, the SKA. The SKA is going to be the largest radio telescope on Earth. It's going to be hundreds of thousands of antennas. It's actually 2 telescopes that observe at different frequencies, higher radio frequencies, with these antennas that will be built in South Africa, and these ones in Australia that will look at very low radio frequencies. So, we're going to find millions of bandjet radio galaxies, much more mini halos, relics. It's going to really change my field of research for sure, and probably yours too, actually. And so it was, Annelies said it in the introduction, but I am part of a team in Granada at IAE that is coordinating the participation of Spain in the SKA, because Spain is actually a member country of the SKA. There's some formal signature agreement pending still, but basically we are members. And so our role is basically to help you eventually make SKA science. So if you want to know more about the SKA, if you want to get involved, there's a science working group that you can join and things like that. So please let me know, and I can help you with this. And this is really coming, right? The SKA is kind of this like long, big project. Is it gonna happen and everything? But it's actually the construction that has started, and we are expecting the first data from the science verification quite soon, 2026, 2027. Not of the full array, right, but of a subset of antennas. And yeah, this is a slide from Wendy Williams. She's a SKA project scientist, and she was visiting us in a meeting that I organized at CEVCAD also. So yeah, so it's actually really coming. And it's almost scary, right? What are we gonna do with all of those sources? On top of that, we have LOFAR that will observe at very low radio frequency, so it's gonna detect even more extended sources probably. And we're gonna have also probably eventually the NGPLA that will cover at higher frequencies. So what are we gonna do with all those observations? I think these are my ideas, right? But I think that the first thing we need to do is to rethink about how we classify these sources. Because as you have seen, it's a bit problematic. Perhaps machine learning is going to help us do that, at least identify those sources. There's already a lot of work. As you know, this field is like really exploding, and this is good because probably we're gonna need it to solve this amount of data that we have. Simulation, this is the simulation video that I was showing is from this paper. It's very important for us to understand, to disentangle all of these projection effects and understand how these particles, the electrons, diffuse inside the intracluster media. And polarization measurement also are very promising. We are starting to do that. I am also starting to work on that with the VLA on for Perseus. From this measurement, you can derive the strength and magnetic fields, of course. And in some cases, you can use rotation measure to infer the 3D structures of the radio emissions. Super promising, as I said, results. And so it's quite exciting. It's not too scary. It's kind of exciting. Yeah. Okay, so as you can see, I think we are really reaching a high level of quality in the radio observation of galaxy cluster, and we are realizing there is a lot more that we can learn from these environments. One thing that I didn't really mention, but all of these radio galaxies, these bench-jet radio galaxies, I think if we study them more, eventually perhaps we can use them to probe the cluster weather, to try to use them as tools to understand better galaxy cluster. And of course, all of this is helping us for future study with the ASKA or with the GBA as well. And that's it. I think I will conclude. Thank you.
Thank you, Marilou, for this very interesting talk. Other questions in the room?
Thank you. Nice talk, Marilou. So I have two questions. First is regarding the IC310, the blazar. So since it's a bright blazar even at radio frequencies, there must be some VLBI observations.
Yeah.
So from those observations, is there a constraint on the inclination angle?
Yes, there is. Yeah. And I got more of these observations, and we see only one jet from those observations. But yes, you can constrain it. I don't remember the number.
Okay. Okay.
Yeah. I don't remember. It's like 20 degrees.
No, so
something like that. I don't.
The projection which you showed, it is based on those numbers? Because, I mean, you showed a schematic that probably we are looking at that particular galaxy from a projection, like from an angle. So was it based on those numbers, or it's just a hypothesis at the moment?
Sorry, I don't understand. Can you repeat the question?
So for the IC310, you gave a schematic, like probably we are looking from this possible angle. So it is inclined at a certain angle with respect to us. So that was a hypothesis, or was it based on?
It's an hypothesis.
Sorry.
But I think that's I mean, it's very unlikely because these jets are so close to each other. For sure, it is somehow projected. We don't know by how much. You can kind of make estimation, like, okay, if it looks like a normal narrow angle tail, then it would be like inclined by this kind of amount. You can make this kind of estimation. But yes, it's a way that we have think about how to, how can we see those two jets and how can we see gamma rays at the same time. But it is strongly motivated even before the blazar thing. I mean, since they are so close to each other, it's for sure some sort of projection effect. It cannot be that extreme bending inside the galaxy.
Okay. The second question is regarding the plethora of data you have acquired for the Perseus from VLA. I know it's a big task. Why have you not gone much lower with LOFAR to get the injection indexes and?
Yeah. Well, there are people that are trying.
Okay.
Yeah. I'm not involved into that, but there's LOFAR observation of the Perseus cluster. It's just so challenging, I think. It's so bright. It's like the worst.
Well, they have handled
target to
they have handled MT7, so I guess
yeah,
it's also could
yeah,
be possible.
I think it's coming. I'm looking forward to the result as well.
Right. All the best. Thanks.
More questions?
Thank you very much for the nice talk. I wonder, why are you talking about the gamma ray emission of IC310 in particular and this blazar problem? Because there are other radio galaxies that has been detected at very high energy gamma rays.
Yeah.
So what is particularly important in this one that makes you?
Is the band jets in this case? I mean, is the fact that we see band jets in this case. So it's the only band jet radio galaxies that I know of. Maybe you know more. We can chat later about that. But it's the only band jet radio galaxy that I know of that has gamma ray emission. So I mean, if it's like this whole projection idea, right? If you have like two jets on one side, why would you see gamma rays? Like we really don't expect that. But maybe there are more, and maybe many, I don't know, maybe other head tails like this are actually showing that, but it's hard to get these gamma ray detection. But it's the only band jet radio galaxy.
Yeah, the very good.
Milo, very nice presentation. So I have a question. In those band jet galaxies, how many have you classified so far as band galaxies? What, even wide tail or narrow?
In the whole
Yeah, the
universe?
population of this.
If I don't know exactly, hundreds, I guess, probably more now. The thing is that this is like very much increasing with the LOFAR surveys and these kind of new radio facilities. So these numbers are really now exploding. Okay, so like 5 years ago, I would say maybe a few hundreds, and now probably much more than that. Like for example, I'm involved in a paper where they study these band jet radio galaxy at, you know, high redshift for me, let's say. And so we are starting really to resolve that. So there's many more now, but I don't have a clear number to them. But there's many. I mean, per cluster, maybe there's a few per cluster. But like, let's say in Perseus, I've showed you many like 4 different ones, but there's much more than that are smaller. And this isn't Perseus because we can detect these small ones because it is so close, right? But imagine that in any cluster further away, we completely miss those ones. And we would have missed probably many, like CR15, probably we could not detect if Perseus was further away. So,
And do you expect
many.
these jets are interacting with the medium? Like there's some gas there, maybe that you could trace maybe with ALMA, or because at the beginning of your talk, you show some region that you observe with ALMA that you are covering now with Megara.
Yeah.
But do you have more cases that you could see this kind of interaction?
I mean, these filaments are very particular to the central galaxy. So these filaments are only around the central galaxy. So band jet radio galaxy, these galaxies are just radio galaxies that are inside the cluster. But in my opinion, any radio galaxy in the galaxy cluster that have radio jets will have some sort of funky morphology, right? Because they are going through the intracluster medium. The intracluster medium is full of motions, and they interact together. And the proof is that we see those band jets, right? So the question is exactly how these things interact can be very complex, and we are finding it now.
Okay,
I don't know if that answers.
Thank you, Marilu. Maybe this is something you cannot measure, but do you have a feeling of how much mass or energy are these jets injecting in the medium? Because you were talking about the sort of the dynamics, the thermodynamics within the cluster being regulated by this. Is it the mass of the amount of mass that you're putting into the cluster where it's creating the trick, or is it the energy that you inject?
I think the mass is very hard to answer because in the end we don't know the content of those relativistic jets, right, in the supermassive black hole. We know that there's electrons, but we don't know anything else. So I don't, perhaps some people, I don't know. I have never done this calculation, but maybe there's some estimation based only on the electron, perhaps, I don't know. For the power that they inject inside the intracluster medium, that's a good question because when you look at the central one, the AGN feedback, you can measure that because you can see those cavities. So you can estimate, I don't have the numbers. Well, it's big, it's very powerful. I don't know the number exactly, but it's like because you can see that they push away the intracluster medium, they makes these holes inside. And so you can measure like how big this is and how much energy is requested to make this. And then you compare to how powerful the jet is, and it matches really, really well. So this is how we know that Asian feedback works. That when you calculate those two things, it matches. So you can, but this has been done only for central galaxies. What I'm wondering about now is that what are those other radio galaxies in the cluster doing? I don't know.
Okay, so let's stop here. Thank you again
Thank
for
you so
answering the
much.
questions. And thank you all for coming, and see you next time on Thursday.